Welcome to section 13.4, Complex Numbers in Polar Form. At the end of this section, we should be able to answer these questions. What is a complex number? How can we represent a complex number graphically? What is the Cartesian format of a complex number? What is the polar form of a complex number? How do we transform complex numbers from Cartesian format to polar format, and vice versa? How do we find the product, quotient, and reciprocal of complex numbers in polar form? What is de Moivre's theorem? And how do we find roots of complex numbers in polar form? Let's start by defining a complex number. Well, first of all, a complex number will be the sum of a real number and an imaginary number, where an imaginary number is defined to be the square root of a negative number. So a complex number will take this form: z equals 4 plus the square root of negative 9. Now, we're going to use I as the unit imaginary number. So we can rewrite this, as we've seen before, as z equals 4 plus I times the square root of 9, or 4 plus 3i. Now, how will we represent this information on a plane? Well, we're going to create a new coordinate system, the complex coordinate system, where our horizontal axis will be real numbers and our vertical axis will be imaginary numbers. So when I'm adding a real and an imaginary number, like 4 plus 3i, I'll move out 4 units along the real axis and then up 3 units along the imaginary axis. So let's review. The unit imaginary number is just going to be I. Now when we square I, we end up with negative 1. The general form of our complex number in Cartesian coordinates will take the form a plus bi, so a real number plus an imaginary number. The real number we'll call the real part, and this b will be the imaginary part. And another concept that will come in handy while we're solving our problems is the complex conjugate of a plus bi, which hopefully we remember to be a minus bi. Now, just as we've discussed earlier in this chapter, any coordinates using two axes, like x and y, can also be described using polar concepts. So this complex number with a real horizontal axis and an imaginary vertical axis can be rewritten with an r and a theta, a distance from the origin and an angle from the horizontal. We're going to use this notation to describe a complex number in polar form. R cis theta, where cis stands for cosine theta and I sine theta. R is going to be our modulus, or the length of our vector, and theta is going to be called the argument of z. So our angle is called the argument. And for these purposes, we can use degrees or radians. So we need to clarify that anytime we're working with the polar form of a complex number. Now, the absolute value of a complex number is also the modulus and the magnitude, just like when we were dealing with vectors. Absolute value, modulus, magnitude. And so that's going to be our distance from the origin in the complex plane. All right, so once again, since we can describe a location or a complex number in two ways, Cartesian and polar, there must be some relationship between the two. And it's very similar to what we did with real numbers and real coordinates. Here, if z equals a plus bi, so 4 units out and 3 units up, if we want to express that in polar form using cosines and sines and a modulus, or r value, length, we can use our right triangle trigonometry concepts again. So A, being the horizontal, turns out to be the hypotenuse times the cosine of theta. And B, the vertical side, turns out to be the hypotenuse, or r, times the sine of theta. And then again with our right triangle Pythagorean relationship, our hypotenuse, r squared, will be the sum of a squared plus b squared, our horizontal and vertical sides of our right triangle. And finally, to find theta, that relationship, we're going to use the arctangent relationship of the opposite over the adjacent. So again, our right triangle trigonometry allows us to convert from Cartesian form to polar form and vice versa.